Today we're going to look at some truly delightful maximum problems. Why I think they're delightful: they look complicated, they involve some magnificent math, and yet we can still solve them. I understand you might have a different way of describing them. So we'll start with finding the point on the line, y equals 6 minus x squared, that is closest to the point 0, 3. And we'll start by drawing ourselves a diagram. We have a parabola upside down raised up 6. The point 0, 3 is not on the line. You can check that. If you put in 0, you do not get 3. So 3, 0, 3 is not on the line. And it'll be below it, and we know that because if this is 6, 3 is down here. The point closest to the line, something like this. Normally we'd call that x and y, but instead of y, we know that y equals 6 minus x squared. So we'll call that x and 6 minus x squared. So what did we do? We picked a point on the line so we could see what we're doing. We would normally call it xy. Y equals 6 minus x squared. So this is the point we're looking for. Now, how do you find the point that's closest? That means you want the shortest possible distance. And we have a formula for the distance between 2 points. So x2, y2 is one of your points. I'm going to make x2, y2 be my point x and 6 minus x squared. x1, y1 is the other point, this one, which is 0, 3. So we'll put 0 in for x1 and 3 in for y1. That gives us the following equation. Now, we might as well clean that up a little. 6 minus 3, and the square root is the exponent 1/2. Time to take a derivative. And why are we taking a derivative? You want the point closest, that means smallest or minimum, and a minimum occurs when the derivative is equal to 0. So we're going to find the derivative. Looks like a chain rule. We'll bring the exponent down, leave the bracket alone, lower the power by 1, and then multiply by the derivative of what's inside. Derivative of x squared is 2x. Then we have another chain rule. Bring the exponent down, leave the bracket alone, lower the power by 1, and multiply by the derivative of what's inside that bracket, and that's where the negative 2x comes from. So we did a chain rule. Exponent comes down, bracket alone, lower power by 1, derivative of inside terms. All right, time to clean that out. I think I would like to move this negative exponent down in the denominator. We already have a 2 in the denominator, so we'll just combine those and put them together. Everything else stays in the top. What else can we do with that? What if we put the 2 and the minus 2x together? All right, and we've let this equal to 0. And why we've let it equal to 0, again, closest minimum occurs when slope equals 0. So we took the slope, or the derivative, and set it equal to 0. I'm going to put this line at the top of the next page. And now what could we do? This denominator is really quite annoying, so let's just get rid of it. If we multiply both sides by that denominator, what will that do for us? See if you can figure that out ahead of me. So I'm multiplying the right-hand side by the denominator and the left-hand side by the denominator. Okay, when we do that, that will eliminate that denominator, which was the entire point of doing it. And on this side, because we have 0, we just get 0 on the left. And this is marvelous. We had this complicated, complex-looking problem. How on earth were we going to solve it? And now it doesn't look bad at all. Let's expand. Multiply the minus 4x in. That gives us minus 12x and positive 4x cubed. We have some like terms. And before we begin, let's make the numbers as small as possible. So what would happen if we divided by 2? So we'll just divide absolutely everything by 2. And I think it's time to factor. We see an x that's common. So pull the x out, multiply by minus 5 plus 2x squared. So either this one is equal to 0 or this one is equal to 0. Solving this one equal to 0, I think I'll bring the 5 over. divide both sides by 2, and then take the square root. All right, so we have plus or minus root 5 over 2, and we always need to draw ourselves a number line to find out what's going on. So the points that we got were 0, positive root 5 over 2, and negative root 5 over 2. You have to check where your slope is positive or negative. So you're plugging points in. I think we can get away with plugging it in here because we have not changed any signs. The denominator that we eliminated comes out of a square root, so it's guaranteed to be positive. So we should just be able to substitute in here. So let's try it. Nice, easy number between 0 and 1. I think I told you what number I want. Nice, easy number between 0 and root 5 over 2 would be 1. When you plug in 1, x is 1, which is positive. 2 times 1 squared minus 5 is a negative. So that would give us a negative in this section. Nice, easy number out here. Oh, how about 10, just to be safe? When we plug in 10, that will be positive. And 10 squared times 2 minus 5, still positive. On the other side, how about negative 1? When we do negative 1, that will be negative. Negative 1 squared times 2 minus 5 is also negative. Negative times a negative is a positive. And I'll work with negative 10 for my next number. Negative 10 for that one is negative. Negative 10 squared times 2 minus 5, that will be positive. Final answer for that one, negative. So there's our plus minus chart. For those who don't like to put in numbers, and I'm one of them, I would graph this. I would say I have an x-intercept of 0, x-intercepts of minus root 5 over 2, root 5 over 2. It's a positive x cubed. The graph would look like this. So I'm just graphing the derivative. And where it's below the axis, it's negative. Where it's above, it's positive. So I would have done it that way. However you do it, this is our plus minus chart. So what do we have? Decreasing, increasing, increasing, decreasing, decreasing, increasing. So I've got a minimum occurring at minus root 5 over 2 and root 5 over 2. And what were we trying to do? Find the points on the line closest to 0, 3. All right, so we know the x value. We want the point on the line. That means we need to calculate the y value. So let's start with x equals root 5 over 2. And I always start with a positive because it's simpler, and maybe there's a quick way of doing the other one. So y would equal 6 minus root 5 over 2 squared. Well, isn't that lovely? So we'll get 6 minus 5 over 2. Okay, get ourselves a common denominator. Multiply that one by 2 and that one by 2. So now I've got 12 over 2 minus 5 over 2, or the whole thing over 2. So I'm getting 7 over 2 for that one. So first point on the graph, closest to the line, closest to the point, root 5 over 2 and 7 over 2. Now, what happens if we put in the negative? If you put in the negative and you square it, we get the same answer. So our 2 points, root 5 over 2, 7 over 2, and negative root 5 over 2, 7 over 2. So those are the 2 points on the line closest to the graph. And feel free to draw it and see if that makes any sense whatsoever. So 7 over 2 is 3.5. So it's saying the y value is here. Well, that does look pretty darn close, doesn't it? Same thing on the other side. So this looks like it makes sense. Should we just do a quick summary? We called the point xy, got an equation, and that was the distance between 2 points, took a derivative, set it equal to 0, picked out the critical points, did the plus minus chart, identified where the minimums were, found the y values of the points. It's really no different than anything we've done before. Well, except the setup makes it look a little more frightening. Okay, let's have some more fun, shall we? An 8-meter fence is 1 meter from a wall. A ladder is leaning against the wall just over the fence. Say what? So 8-meter fence, here's that, is 1 meter from a wall. And there's our ladder that leans just over the wall. And we want the shortest length of this ladder right here. So this is our ladder. Well, doesn't this look interesting? I think the first thing I would do is put an angle in at the bottom. And if you look at this picture, this angle in this triangle with a right angle, would it not have to match the angle up here? I'm quite sure it would. I think there's a theorem when you form an F. So this is what I'm looking at. I'm looking at the F formed by these. I believe those are called corresponding angles, and corresponding angles are equal. So we have 2 equal angles. This is good because we don't really have anything else. Let's look at 2 separate triangles, shall we? So I think we want to look at this triangle, and then we want to look at the triangle in the bottom. So those are the 2 triangles we're going to look at. They both have an angle in theta, which is good. They both have a couple of sides in them that we know. And then they have a missing side that we're going to deal with in a minute. So in the blue triangle, we have an 8 and a theta. The red triangle, this distance is 1. And let's call the missing sides x and y. So focusing up here, theta is the angle in the corner. We have the hypotenuse and we have the adjacent side. So adjacent hypotenuse, that would be cosine. Cosine theta is adjacent over hypotenuse. If you multiply both sides by x to eliminate the denominator, we'll get x cos theta is 1. And then if we divide both sides by cosine, you'll be able to figure out what x is. So x is equal to 1 over cos. So this part of the ladder we can call 1 over cos theta. All right, let's keep going. Let's do the exact same thing with the blue one, shall we? With the blue triangle, we have theta opposite and hypotenuse. So opposite and hypotenuse, that would be sine. Sine is opposite side over hypotenuse. Let's multiply both sides by y. When we do that, y sine theta equals 8. Divide by sine, and we'll get y equals 8 over sine theta. Sorry, that should be an 8. So 8 over sine theta. Okay, what does that do for us? Why do we care? Determine the minimum length of the ladder. So again, this is the ladder. The length of the ladder is x plus y. And x was 1 over cos theta, and y was 8 over sine theta. So again, because the length of the ladder is x plus y, we can write it this way. And then minimum means derivative equals 0. Don't panic, it's nowhere near as bad as you think. Little quotient rule here, derivative of top times bottom. Derivative of top times bottom minus top, derivative of bottom, all over bottom squared. And do the same thing with this one, derivative of top times bottom, minus top, derivative of bottom, all over bottom squared. So derivative of top was 0 times bottom minus top, derivative sine is cos, bottom squared. We're going to let that equal 0. Let's deal with the 2 negative signs. And then what? Perhaps we should bring that 8 cos theta over sine squared theta. Bring that over here. And I think I'd be tempted to multiply both sides by sine squared cos squared. And the reason I would do that is to clear out both denominators at the same time. Let's divide by sine squared cos squared and sine squared cos squared. So that will eliminate this denominator and eliminate this denominator. So sine cubed on this side and 8 cos cubed on the other. That's a pretty complicated equation to solve. So what if we divided by cosine cubed? What would that do for us? And you're thinking, didn't we just multiply by things? Yeah. But sometimes you need to collect terms and then divide again. So what does that do? 8 equals, and what's sine over cosine? Tangent. And now doesn't that look better? And again, the marvelousness of this math. It was so complicated and now doesn't look so bad. To solve this, we could take the cube root. And when we take the cube root, I would get 2 equals tangent. This is not one of your special triangles. So we would do second function tangent, and the calculator would tell us 63 degrees. Now, there are other answers where else is tangent positive, this quadrant, but think about that one. We're finding this angle right here. This angle must be less than 90 degrees, otherwise your ladder is going over here. So I'm not even going to waste my time finding that other angle. But we are going to determine where that is on a plus minus chart. That sounds like good fun too, doesn't it? Okay, here we go. We have an angle of 63 degrees, and we're trying to figure out whether the derivative, which looked like this, is positive or negative. Not nearly as bad as you think. It's a nice, easy angle over here. When we take 45 degrees, sine and cosine are the same size. So if sine and cosine are the same size, can I call it A just for the moment? Then that would be an A and an A cubed. And that would be an A and an A cubed. A squared, sorry. So if I have A over A squared minus 8A over A squared, I'm pretty sure that's negative. So what did we do again? We said at 45 degrees, these two are the exact same size. Calling it A, just so I don't have to think too much about sines and coses. A over A squared minus 8A over A squared, definitely negative. So at least one of them wasn't so bad. All right, and then you're going to have to do the other one. So put in a nice angle on the right-hand side of 63 degrees. I know you might be tempted to use 90, but we can't. The reason we can't is cosine of 90 is 0. So I'm afraid this is calculator time. Just pick an angle on the right, maybe 75 degrees. Plug it in, chung, 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 and calculator says positive. And so we have a minimum at 63.43 degrees. Does that answer the question? Determine the minimum length of the ladder. All right, this was the length of the ladder. So the length of the ladder, we're going to put in the 63.43. And again, haul out your calculator. You will eventually get to an answer of 11.18. So what we know is the minimum length of this ladder that reaches to the wall is 11.18 meters. Whew, that was glorious. So quick recap, what happened? We drew a picture, we drew two triangles, we introduced an angle, we set up sine and cosine. And how do you know to do this? Well, you don't really, but after you do a bunch, you will. Our aim was this. Our aim was to get an equation with only one variable. And with questions like these, when you have x's and y's, the way to get around it is to start looking at angles, because the angle will be the same, and then you only have one variable on the right. We took a derivative, set it equal to 0, got our sines and coses together, and then realized that dividing by cos would give us tangent. We could solve it, plugged it into our plus minus chart, find out where the minimum occurs, put theta back in, and get ourselves an answer. Okay, your job. Lesson 6. Start at question 20. They're not that bad. I think question 20, I even just give you an equation and say find the derivative. And then they get fun after that. So you just do as many as you can. We're going to be very different in how many we think we can do, but I think they're magnificent. And, some of you might as well. Have fun.